All right, what the heck? Let's do 19 and 20.2. So we have a vector field f and a curve c that we're trying to integrate over, right? So we're trying to do a line integral. C is this bizarre circle. So C is a circle, radius 2, in x plus y plus z is 3, right? And it's centered at, what, 1, 1, 1 or something? Okay, so if you see that video for the other problem, there's drawing a picture of this, and it's a shitty picture, so I'm just not going to do it again. Cool? So, I have a line integral. I should probably turn that into a surface integral, because I just learned this new trick, right? What the hell? Let's hit it with Stokes. Oh, I need to tell you what the vector field is, too. So I'm going to hit it with Stokes, and I'm going to get a curl of f dotted with the area. And they told me f was, what, minus y, x, and z? Okay, so first things first, I should check all the assumptions of Stokes in order to hit this with Stokes, right? Let's assume that they're all satisfied because they are. You can go through and check them all if you want, but they are all satisfied.
We proved it in 21.
Yeah. So it's in the video for 21 if you want to go check. Okay, so I want to calculate a curl for this thing, right? Okay. What did you guys get?
It ends up being 0, I, 0 minus 0, 0 minus 0 for j, and then 1 minus a negative 1 for, yeah.
Okay, so all told, you get 0, 0, 2. Okay? And then you're like, hey, that'll be chill, right? Because this will be the integral over the surface of 0, 0, 2 dotted with the area, which will be super duper easy, right?
At first, except the...
Yeah, except it's a pain in the ass to parameterize this thing, right? So let me notice, like, I'm going to look at d area, and I'm going to think to myself, that thing is what?
Normal vector on some sort of scale.
Yeah, it's a unit normal times, and this is scalar multiplied, right, by the area. Really, this is true for patches, right? Like, the way you do a surface integral is you split the surface up into a bunch of little patches, and then you wonder how much stuff's flowing through this patch, right? So you take your vector field, you dot it with a unit normal to figure out how much they agree, and then you multiply it by the area of the patch to figure how much stuff is flowing through the patch. But on this problem, what am I integrating that's special? What's my vector field here?
Vector field is 0, 0, 2, which means it only has a z.
Yeah, it only has a z component, and it's a constant z component, right? So this vector field always points the same direction and the same amount. What's special about my surface? I have a circle in a plane centered somewhere, right? What's special about that thing? It's flat. So it always has the same normal vector, right? So you can get away with saying, hey, it's not approximately a unit normal times an area. It actually is just straight up the unit normal times the area. You guys see that? So this thing, I can really just use a little geometry to say that's going to be the vector 0, 0, 2 dotted with, this guy better be a unit normal. And then what's the area of a radius 2 circle? Pretty sure pi r squared works even when it's at an angle, right?
Because the radius is still on the plane.
Yeah, the radius is on this plane, but who cares, right? The area of that circle, wherever it sits in space, is 4 pi right? Really, pi times 2 squared. Okay, now, what's your unit normal? Yeah, it should be 1, 1, 1, right?
Yeah.
But 1, 1, 1 is not a unit normal. It's just a normal. Where did you get the 1, 1, 1? What did you peel that off of? Plane?
Oh, no, yeah, it's x, y, and z.
Yeah, you guys remember that? That's these components. That's 1, 1, and 1. They all have to be on the same side equal to a number. You guys remember that?
Okay.
Okay, so you peel those off. There's your normal vector to a plane. Bam. But it's not a unit normal. So how long is it? Yeah, it's square root of 3 long. So I need to divide by the square root of 3 to get that magnitude. You guys see that? So when you do this dot product, actually that's a good question. Should you scalar multiply first or do the dot product first? What does the order of operations say?
Multiplication and division kind of act at the same time. So.
You should probably dot first.
Yeah, so this is a good example for you all have lost some stuff, right?
Yep.
Does the T stand for dot?
Parentheses.
What?
No. But,
There are parentheses?
but it's
Well, those are
type of mail.
Okay, so pitch this thing, and then do something reasonable. And then something reasonable is they're both multiplication. One is a dot product, like a vector category of multiplication, and the other one's scalar multiplication. They have the same priority. You can do either first, and it won't matter. I would do the dot product first here for aesthetic reasons.
That scalar just distributes through, which carries through the dot product anyway. So
Yeah. You do eventually get, so you get a 2 out of this guy, right, out of the dot product. So you get a 2 times 4 is an 8, and then there's a pi, and then there's an over the square root of 3. Boom, boom, boom. And please note that when I use Stokes, I calculated an orientation here. You guys all see that? And I should spend a second worried about whether this is plus or minus 8 times pi over the square root of 3. You guys see that? So
that should.
they told me this. They told me that there was a circle centered at 1, 1, 1 in a plane, and that it was oriented clockwise when viewed from the origin. You guys see that? So here's 0, 0, 0. Here's your point, 1, 1, 1. Someplace around this thing is a circle in a plane. And that is clockwise when viewed from 0, 0, 0, assuming you're seeing this picture the same way I am. You guys see that? Which is that this is the close side of the circle, and that's the far side of the circle. You guys cool with that?
Yeah.
So that would be this guy, right? Okay, now which orientation did I pick for my normal vector? I need to make sure that goes with the right-hand rule here. So I picked 1, 1, 1 as my normal vector, right? Which points that way. And so if I'm going around my circle, I'm going around my circle like this, and that orientation, do those right-hand rule together? Yep. Cool. Plus. Cool. Question, Steele?
Wait, does that mean we don't really have to call like the two? How do I even phrase this?
I don't know.
Sorry. For the area, finding it being 4 pi, is that accounting for the S, the
Yeah.
surface area?
So that's me accounting for this integral kind of manually, right?
Yeah, I just want to make sure of that.
Like normally I would come up with a parameterization, I would crank on that thing, right? So if I was going to do this like in the least elegant and most cranky way, I would parameterize my surface, right? So I would come up with some like R of X and Y, right? For that disk. You guys see that? That would be this disk in here. We'd come up with an R of x and y, and then my D area would be Rx crossed with Ry, dx, dy, right? And we'd need to put some bounds on this sucker, and it would probably suck a lot.
The bounds would be the worst part.
Yeah, the bounds are going to be kind of nasty, because they're going to be an ellipse when you project a circle down. You guys see that? Like you have a tilted circle in some plane. When you smash vertically, you're probably going to get an ellipse. Cool, cool?
Yeah.
And so then your bounds will be horrible. But you can just eyeball it this way instead. I would recommend towards the eyeball it whenever possible. Cool?